Hello. Hi, everyone. So in today's live stream, I will talk about titrations. So this live stream, it works for both IB and A-level students, okay? Still keeping my live streams private for now, because I don't know, for now it's private, but then at some point I'll probably make it live, really live. So, all right, so titrations. I think what we'll do, again, I don't have much time because I have lessons starting, but what I want to do is I want to quickly explain just the very easy titration question and then gradually work through to more difficult titration questions with dilutions and stuff. So we'll start with an easy one, and then as we continue, the questions would become more and more difficult. And I really wanted to make this stream about back titration because this is like the most common stoichiometry questions everyone asks. But I thought that I cannot discuss really back titrations before we practice regular titrations first. Yeah, so let's try to do it this way. So today I would try to explain as much as I can within those 30 minutes that I have about normal titration. And then hopefully maybe next stream or at some other point, I would focus on back titration questions. I hope that's fine. Right, so in general, what is titration? Well, I think everyone knows what it is. Yes, so I'll just quickly explain that. In the titration, you have a substance, one substance would have a known concentration, another one would have an unknown concentration, and they would react. So, for example, you can place your analyte of an unknown concentration to the conical flask, and you could place the substance of the known concentration into the burette. Yeah, and then also to the conical flask, you would add an indicator that would change the color once whatever is in your burette would react with would exactly react with everything that is in your conical flask. Yeah, so that point of time, like what you'll be doing is you'll be dropping down the substance from the burette drop by drop, and it would react with the substance that is in your conical flask. And then when all the substance in the conical flask has reacted, like in that moment of time, the indicator would change the color. It should be a wisely chosen indicator, so that we are not discussing that just yet. But the main point is that you would know the volume that you've added. Yeah, so the volume of the substance that is in the burette that was required to react with everything in your conical flask. Yeah, with all the moles that are in your conical flask. And the burette is essentially, what is the burette? The burette is essentially just a pipette with a tap, but the readings are sort of inverted. So you have 0 at the top and like 50 or 25, whatever, at the bottom. So why is it so? So it's done like that so that you can measure the volume that you've dropped down, right? So if you start at 0 and end with like 45, for example, you know that 45 cubic centimeters have been dropped down. So we're required to react with whatever is in the conical flask. I hope that's fine, right? Obviously, you don't have to start at 0, so you don't have to fill the burette up to 0, so you can fill it up to some other value and then just subtract. Yeah, so for example, in this case, so we started here, the burette, the meniscus was here, and all of this volume, yeah, so this is the volume that you dropped down. So you can always calculate by subtracting the final minus initial burette readings. Right. So the first question, this question could even be good for GCSE. Let's start with this one. So 50 cubic centimeters of HCl is titrated with 0.05 mole per cubic decimeter NaOH. The initial burette reading was for sodium hydroxide was 0.1, the final 23.25. Calculate the concentration of HCl. So let's see what's happening. So what's happening is you have NaOH in the burette, right? So this is your NaOH. And in the conical flask, you have, it doesn't have to be conical flask, by the way, yeah, so beaker would work just fine. So you have what? You have HCl. And what do we know? We know everything about NaOH, right? So we know its concentration. So we know that concentration is 0.05. We know that the volume, okay, about the volume. So what's the volume? So if the initial burette reading was 0.10, the final was 23.25, then the volume that we drop down would be 23.15, right? So it's So volume of NaOH would be 23.25 minus 0.10. Yeah, I hope you get it. So because imagine this is, let's say, 0.1, and this is, well, I know it's whatever, that was 23.25, right? So what volume did drop down? Well, this volume. So the difference, right? It didn't start at 0. If we started at 0, it would have been 23.25. But we started at 0.10, so that's the difference. Yeah, so final minus initial. And that is 23.15. That's my mental math, so I think it's fine. So we know this about NaOH, and what do we know about HCl? Well, only the volume. Yeah, so we know that the volume for HCl is 50 cubic centimeters. Okay, then, so for titration questions, we always need to know the reaction. Here, the reaction is not given, but obviously you need to know how HCl reacts with NaOH. So it's HCl and NaOH. If you don't know it, you need to revise MYP or GCSE chemistry, whatever you were doing, because this is like pre-IB and pre-A level knowledge. So they react in 1-to-1 ratio. You get acid and base, you get salt and water. Right, well, what can we do? We can find, so you always start the titration questions by finding moles of something, yeah? So they would always give you the concentration and the volume for one of the substances. Usually they give it at the end of the question. Well, this question is very short, so like it's just somewhere there, but normally if there is a lot of text, that information would be at the end, usually, but we'll see. More complicated questions. So here, what do we know? We know concentration for NaOH, we know volume for NaOH, we can find the moles. And also, even if the question is very complicated, yeah, if a lot of things are going on, and you don't have time to solve it and like figure out what's happening, just try to spot the concentration and the volume that refers to that substance, well, to that concentration, and just find the moles, and that's 1 mark. So you can get 1 mark of a very, very complicated question just by finding the moles, okay? That's not a good way to solve the exam, but if you're running out of time, yeah, that's what you can do. Right, so the first thing that we would do is we would find moles of NaOH. Why NaOH? Well, because I know C and V, concentration and volume. The formula to find the moles is C times V. That I'm not explaining, but it's like, I hope you know this. Okay, so moles, it's concentration times volume. Volume must be in cubic decimeters. So we do 0.05 times 23.15 over 1,000. That I converted to a dm cubed. Yes, to convert to dm cubed, you need to divide by cm cubed by the 1,000 over 0.023, not that, times 0.02315. That is 1.16 times 10 to the negative 3 moles. That's moles of NaOH, and then we're applying the molar ratio. So if you needed that amount of moles of NaOH to react, it means that you had the exact same amount of moles of HCl in the conical flask, right? So now you're applying the ratio, it's 1-to-1. So which means that moles of HCl, it's also 1.16 times 10 to the negative 3 moles. Let me just check that I've multiplied correctly. And it's always a good idea to check your calculation twice. Yeah, just as you're just plug this into the calculator twice, just in case. Okay, and then next. So now, what do we know now? So now we found the moles of HCl here. So now we know that in that conical flask, we have 1.16 times 10 to the minus 3 moles of HCl. Well, and then what? Then what do we need to find? We need to find concentration of HCl. I would assume it's mole per cubic decimeter. That's like the default units for concentration. So now I am using the formula for concentration. So it's just N over V. It's essentially the same formula, N equals to CV, but I rearrange it for the concentration. Moles over volume. So that's 1.16 times 10 to the negative 3 divided by the volume of the acid now, right? Because we're finding the concentration of HCl, so we're taking the moles of HCl and the volume of HCl. And that in cubic decimeters, it's 0.050. That's divided by 1,000. So I divided by 1,000. Okay, 1.16 times 10 minus 3 divided by 0.05 is 0.0232. Mole per cubic decimeter, right? Okay, so what did we do? We found the moles of NaOH first, yeah, because we knew its concentration and volume. Then we applied the molar ratio to find the moles of HCl in the conical flask, and then we found the concentration of HCl by doing moles over volume. Right, this is like the most common question that they could ask, yeah, so the easiest one. Then, next question. The carbonate of metal M has the formula M2CO3. A sample of M2CO3 of mass 0.394 grams required the addition of 21.7 of a 0.263 mole per cubic decimeter solution of hydrochloric acid for a complete reaction. Calculate the relative formula mass of M2CO3 and therefore deduce the identity of M. Right, so let's do this one. So what's happening here is, I could draw it out. Yeah, so usually even if I'm solving questions, I'm trying to draw it out. But I'm not sure if you don't have to do it. Yeah, so I'll just draw it out to see, to approximately like understand what's happening, what is added where. Yeah, so let's do it. So they take the solid M2CO3. Obviously, you don't get any extra marks for that. Yeah, so they took solid piece of M2CO3 for which we know the mass, which is 0.394 grams. And then they probably, well, they either dissolve it or just titrate it as it is, probably dissolve. Yeah, so let's say that they take it and then they titrate it. Yeah, so I'll just place it here. And then they titrate it with HCl. And we know everything about HCl. So we know its volume and we know its concentration. Fine. Okay. Then what do we need to find? So we need to find the relative formula mass. So how do we do it? So basically, we need to know two formulas for this question. So first is the same as in the previous. So moles, it's C times V, right? And then another formula for moles, it's N equals to M over MR, mass over relative molar mass. So these two formulas we would need. MR usually we find from the periodic table, but obviously in this case we cannot do this because we don't know the metal, and that's why they ask us to find the MR, right? We don't know, we cannot find it from the periodic table because the metal is unknown. And if you just rearrange this formula, you would say that MR, it's M over N, right? So we know this number, it's 0.394. And what we need to find is we need to find the number of moles of M2CO3. Then we would be able to find the mass. And the moles we will be finding from the titration. Okay. So what is missing for the titration? Well, we are missing the equation, right? So we know that M2CO3, it is reacting with HCl. That's what's happening here in the titration. Yeah, so HCl, when it's added to M2CO3, they would react. This is metal carbonate with HCl. Again, this is, well, kind of MYP or GCSE knowledge, right? So you know that when metal carbonates react with HCl, you form a chloride of that metal. So you would form MCl. Why is it MCl? Because CO3 has the charge of 2 minus, and since the formula is M2CO3, it means that the charge of M is 1 plus, right? Because you have two M pluses to cancel out the 2 minus of the CO3. And if it's plus 1, you know that Cl is 1 minus, so it must be MCl. Or you can just think about it as a metal of group 1, because metals of group 1 would form M2CO3 salts. Right, that we know. And then, so when metal carbonate reacts with hydrochloric acid, so you get the chloride of that metal, you get bubbles of CO2 gas and H2O. Again, this is a prior knowledge for both A level and IB. So that is something that you should have known by now somehow from your previous chemistry studies. Okay, then we need to balance it. So I'm balancing. I have one metal on the left, two metals on the left, one metal on the right. So I put a 2 here to balance metal. Then to balance chlorine, I put 2 in front of HCl to make it 2. And that's it, I think. Yeah, so it's 2 hydrogens on the left, 2 on the right, 3 oxygens on the left, 2 plus 1, 3 on the right. So all good. You see, so the metal carbonate reacts with HCl in 1:2 ratio. Fine. Okay, and then essentially the rest of the question I will be doing in exactly the same way as the previous one. So I know the concentration and volume for HCl, yeah, so you always start from there. So if you always try to find some volume and concentration that are given for the same substance, yeah, and just find the moles. So first thing I would do is I would find the moles of HCl. So I'm using this formula that moles at C times V. Concentration is 0.263. Volume is 21.7 divided by 1000, right? Because I need to convert it to dm cubed. So in this formula, because the concentration it's per dm cubed, you need to use a volume in dm cubed. Yes, you always convert cm to dm cubed. Times 0.0217. So that is 5.71 times 10 to the negative 3 moles. That's the moles of HCl. Then I can find the moles of M2CO3. Yeah, and those moles would be coming from that solid piece, right? So now that I will find the moles of M2CO3, that's what I wanted to find in the first place. Okay, so I find moles of M2CO3 using the ratio of HCl to M2CO3. So it's 2:1 ratio, which means that I have twice less M2CO3 than I have HCl, right? Because one coefficient in front of M2CO3, which is 1, if nothing is written then it's 1, is twice lower than the coefficient for HCl. So the moles of M2CO3 would be 571 times 10 to the minus 3 over 2. 71 times 10 to the minus 3 over 2, which is 2, 8. Well, I put 5, but I mean, again, about the rounding, yeah? So I'm now, well, I put as 6. I'm now kind of using IB guidelines. For A level, depending on the board, you don't really have to round the intermediate calculations, right? So here you could have written the full answer. If you're doing IB, it's better to round. Yeah, so it's better to use it as like 3 significant figures. But again, not necessarily, right? So usually they would give the range of answers. I'm rounding, but it depends on the board and on the program, whether you should round or not. And even if you round or don't round, the maximum you could lose is you could lose a mark if you're using too few significant figures, or if you're rounding it wrong. Yes, if you're rounding right, you normally don't lose marks. Okay, so that's the moles of M2CO3. And then what? Well, and that's it. And then I find the MR. Yes, so I find MR of M2CO3 as mass of M2CO3 over moles. So it's 0.394 over 286 times 10 to the negative 3. Let's see, so 0.394 over 00286, which is 137.8. Yeah, 0.8, 37.8. And then okay, and well, approximately 138, right? And then what do we do? Then we need to find the molar mass of the metal, right? Relative formula mass we found. Therefore, okay, to deduce the identity of metal M, what do we do? We just okay. Let's say that relative atomic mass of metal M is X. Yeah, we can say that. So relative atomic mass of metal A is X. Then we would have 2X. That's molar mass of 2M. Yeah, then plus 12, which is molar mass of a carbon. Again, if you're doing IB, you have to put molar masses to two decimal places. Yeah, so for instead of 12, you would write 12.01. For A level, it's fine. And 16 times 3, that's oxygen. So that's molar mass of M2CO3, and I know it equals to 138. And then you do 2x equals 2. So I'm just solving it for x. Minus 12, which is 78. And x is 78 divided by 2 is 39. And then you can go to the periodic table, which I don't have it open, but like if now you can check the periodic table and find an element with relative atomic mass of 39, and you'll see that this is potassium. Yeah, so this is potassium. Actually, maybe I can open it. Let's see. No, yes. Let's try to open. I'll show you the periodic table. So, how does it this way? Okay. Yeah, so you see 39.10. Yeah, that's relative atomic mass, so that's potassium. Again, depending on how you round intermediate calculations, you might have a slightly different answer, but if the exam board is okay, normally like for international boards it's fine, they accept a range of answers for all the intermediate calculations and the final ones as well. And these questions are really good in terms of you know whether you've done it correctly, right? Because if you ended up with the molar mass, which is not in the periodic table or which is not a group 1 metal, potassium was group 1, by the way, right? So it's good because we know that it would form K2CO3. If you ended up with something else, with the molar mass that is not there, or with some metal that is not in group 1, which is unlikely but still could happen, yeah, then you know that you've done it wrong. Because if your answer is the number, you never know whether it's correct or wrong. But with these types of questions, you know. Right, next question is this one. So this actually, it also works for both GCS, for IB and A level. And in IB, it's biochemical oxygen demand. Yeah, so there is even specific topic, which I actually don't remember if it was excluded or not from the syllabus. Maybe it was, but it's just a titration question, so still you can practice with this. In IB also, they really like questions where you have like several steps first in the reaction, and then the final step is the titration. In A level also they like those. So this is a it's not difficult, but it's usually like this one. This question is 4 marks, for example. Okay, well, let's see. So the dissolved oxygen concentration in rivers and lakes is important for aquatic life. If it falls, okay, this is just an importance, yeah, of how important it is to find the dissolved oxygen concentration. Now let's read the main part. So a sample of river water is shaken with aqueous Mn2+ and aqueous alkali. The dissolved oxygen oxidizes that to that, forming a pale brown precipitate. Okay, so basically what do they give you? They take the sample of water which has dissolved oxygen in it, yeah, so oxygen aqueous, and then they add something. So they add like manganese 2+ in basic conditions to form MnOH3. And then that MnOH3 is reacted with excess potassium iodide, which is oxidized to iodine. So then they take that and make it undergo another reaction to form iodine, and then that iodine, the iodine formed, is then determined by titration, yeah, and then that iodine that's formed, it's titrated with Na2S2O3. So you see what's happening. This could be any question, yeah, so it doesn't have to be about oxygen. So basically what do they do? So in this question they take a sample of water with oxygen dissolved, and then there are several reactions that are happening. So the first reaction happens, the second reaction happens, and eventually you get iodine that you can titrate. These reactions can be anything, yeah. So it's a very common question when you have substance for which you need to find out the concentration. So you do several reactions, get something that you can get something that you can titrate, and then your last step would be titration. Yeah, so like here, you want to find the oxygen concentration, you do some reactions with it to get iodine in molar, like, because why are they doing this is because iodine that is formed, it's formed in certain molar ratios. Yeah, so they know the molar ratios for every reaction, and so they can track back that iodine to the substance for which you need to find the concentration. And the final step is titration. Yeah, so you got iodine somehow with certain molar ratios, and then that iodine is titrated. Okay. Now let's see, a 25 cubic centimeter sample of river water was analyzed using the procedure above. The titration required 24.6 cubic centimeters of that concentration Na2S2O3. Calculate DOC in mg per dm cube. The DOC was dissolved oxygen concentration. Yeah, so you need to find the concentration of oxygen in milligrams per cubic decimeter. So how do we approach it? Well, again, we scan, it's a lot of text, yeah, so that's a lot of text, but then you always need to spot the concentration and the related volume. Yeah, so here, you see what they give us. They give us the concentration of Na2S2O3 and its volume. So again, even if you're running out of time, even if you don't have the time to read the question, just find the moles, C times V. 1 mark is yours, okay, out of 4, which is 25% in less than 30 seconds. Right, so finding moles of Na2S2O3 C times V, 0.00100 times 24.6 over 1,000, which is, I could do it without the calculator, but I don't want to do it without, because if I mess up, I'd have to not upload this stream, not make it public. Okay, so this is moles. Right, so this is the moles of Na2S2O3. And again, in these questions, usually they would give you, like, you start from the end, yeah, because the end equation, the final equation is the titration, so you're working like from the bottom towards the top equation where you have the oxygen which you need to find. So what do we know? So now we know that we have 2.46 times 10 to the minus 5 moles of S2O3 2 minus. Yes, so you do understand that Na2S2O3, when you dissolve it, sodium plus is released. And so in aqueous solution, you would have S2O3 2 minus, right? This part. It's the same. Okay. Now, what can we find from there? Now you have to analyze the equation. So we had, let's see what happened. So we had Mn, like we had oxygen reacting with something, MnOH3 was formed, and then that MnOH3 was like transferred to the second step. Yeah, so all the moles that were formed here, they were transferred to the next reaction and reacted with I minus. And then the iodine that was formed, it was transferred in the next step. So you have to identify the substances that are kind of transferring to the next step. So here it was MnOH3. Yeah, there it is. Then iodine was formed and iodine was titrated. Yeah. So now we can find the moles of iodine using the ratio with Na2 with S2O3. Why do I'm finding iodine, not something else? Well, because iodine was the one that was transferred from the previous step. So I can find the moles of iodine, which is in a 2-to-1 ratio, so it's twice less than Na2S2O3, so divided by 2. And then it's the same as in the previous step, and you don't even care about the coefficients, right? So coefficients, you cannot look at coefficients when you're using different equations. So you just know that all that iodine, no matter what coefficient it has here, it came from the previous step. So you know that the moles of iodine here is 123 times 10 to the minus 5 moles. And then now in this equation, it's one equation, so you can apply molar ratio to MnOH3. So now you find the moles of MnOH3. Why MnOH3? Well, because that's the link, yeah, with the previous. So that's the substance that was transferred from the previous equation. I don't need I minus because I minus don't lead me anywhere. It wasn't here. Yeah, so I don't care about I minus, but MnOH3 is what was transferred, so I can go back to the first equation using MnOH3. Okay, so MnOH3 has the ratio of 2 to 1, so it means that it's twice more than iodine, so it's 123 times 10 to the minus 5 times 2, so again 246 times 10 to the minus 5 moles. So that I know, yeah, so 246 times 10 to the minus 5. And this is the same amount, so all those moles were formed in the first reaction, yeah, so you see, I'm not taking into account the coefficients here yet. Yeah, because if it's 2 and this is 4, it doesn't matter because these are two different equations. I know that however many molecules or moles I formed in the first reaction, all of them were transferred there. And finally, I can find the ratio of O2 to MnOH3, yeah, because they're in the one equation, in the same equation. So now I know that my moles of oxygen are 4 times less, yeah, 1 to 4 ratio, than MnOH3. It's 246 times 10 to the minus 5. That's a 5. Well, you'll get used to my handwriting, so over 4. So that's times 2, that over 4, which is 6.15. 6.15 times 10 to the negative 6 moles. So that's it. So I found the moles of oxygen in my 25 cubic centimeter sample. Right, and then I need it in milligrams per cubic decimeter. So now I can find well, I mean, from here you can do it in different ways. So let's first find moles per cubic decimeter, yeah? So I know the moles of oxygen in that volume, so I can find concentration of oxygen as moles over volume first. 10 to the minus 6, the volume is 25, so in cubic decimeters it's 0.025, which is 246. 46 times 10 to the negative 4 mole per cubic decimeter. And then, well, this is how many moles I have in 1 cubic decimeter, and I need to find how many milligrams I have in a cubic decimeter. So if I multiply it by, let's do it in grams per cubic decimeter first. So this is how many moles I have in 1 dm cubed. So to find how many grams I have, well, I have to multiply by molar mass of oxygen, right? Because mass, it's moles times mR, right? This you remember, I hope. These formulas have to be learned like I don't know, like a multiplication table or something. You don't have to think about them, you just have to know them really, really well. So times 32. Times 32, so that is 7.872 times 10 to the minus 3 grams per cubic decimeter, right? Why is per cubic decimeter? Well, because that is GDM cubed minus 3. So this was how many moles you have in 1 dm cubed. Well, if I multiply by molar mass, it's how many grams I have in dm cubed. And that's exactly what it says, how many grams you have per cubic decimeter. And then I just have to convert it to milligrams, yeah, because they want milligrams. To convert from grams to milligrams, you multiply by 1,000. So I multiply this by 1,000. So 10 to the minus 3 would be gone per dm cubed. And I had the answer from Mark's scheme there. Yes, so that's correct, 7.872. Okay, well, that's it. I did have another question about dilutions, which we don't have time to do it now because I have the lesson starting, but I hope it was helpful. If you have any interesting titration problems, you can send them. Maybe, I don't promise, but maybe I can include them to one of the streams. And then I hope I will be able to explain more about dilutions next time, and probably back titrations, because that's the most requested topic for stoichiometry. Okay, so see you next time.